So the theorem that I will talk about is this. Niyogi-Smale-Weinberger. So the idea of this talk is more or less introduce this theorem and more or less show which are the ideas and elements that are inside it, and then maybe then, if there is time, to give a sketch of a proof of one of the versions of this theorem. Okay. So in 1880. So the context of this thing, or motivation. So in 1886, we have this art movement, pointillism. So that is made by Seurat and Paul Signac. So essentially this thing is based on you have a certain image that possibly is continuous. So imagine that here we have a tree. Okay, so this is a nice tree with the branches here. And we want to represent this. So essentially what we do is this is the classical thing that has been already seen. So instead of painting it in a continuous way, and more or less you can recover the tree, which is the continuous image, by only using like a set of discrete points in order to represent the object. So essentially this is just a principle that what tells us is continuous objects can be approximated by discrete clouds of points. Okay. So once this, in a way, wherever this principle is seen, which is seen in any TV screen or any digital image that you use, the big problem that emerges, at least mathematically, is if you approximate with sufficiently close clouds of points, you get the image, you get approximations, but you get certain questions. That one of the first questions is under which conditions does a cloud of points capture, whatever that means, a geometrical object. And then another question is how many points. Okay, so more or less this is like many questions that are in topological data analysis under this name of persistent homology, variant, etc. But what is important to take into account now will be, we have a set of points, and this was not until 2008 when Niyogi-Smale-Weinberger they essentially developed this approximation theorem in which they give sort of sufficient conditions that are not necessary. So in order to introduce this has like essentially 3 ingredients. One of these ingredients is what means the topological information that a cloud of points has. The other thing is the reach. And the last one, and the other one is what means to approximate an object by a cloud of points. So first we start with the first ingredient. So essentially is topological information in a cloud of points. Okay. So imagine that we have here groups of points, whatever this is. So one way in which one can try to attach information to this cloud of points is by essentially thickening the points. So I have the points, and what I want to do is thicken the points. So instead of having something that is just discrete, maybe I get something continuous. So in this case will be something of this form. So we pass from this object on the left that is discrete to this object on the right that is more continuous. So essentially what we will have is we have this X, which is a cloud of points. And we will just pass to this that I will call U of X of, let's put here R. It is just a set of points such that distance from P to this is less than R, which can also be seen that is equal to just the union of all the balls around here of radius R. So the idea is that this is discrete, and this is non-discrete. Of course, one of the things that one can see in this setting is that the size of epsilon matters. So this is the first observation. If we start with a very small epsilon, we just get a set of isolated points. But if we get to a very big epsilon, essentially what we have is just a ball. So nothing interesting happened in the two extreme cases. And also there one could consider variations in which instead of thickening each point with the same size, you thicken the points by different radius. But this I will not deal with this case here. So another thing is, we have this cloud of points. Why the topology of this in a way is treatable? Because in principle you look this thing and you are you have substitute this cloud by this object I don't know even how to deal with it. So one of the things that here comes is what is called the Signac complex, which is just like the simplicial complex that you take your favorite, this cloud of points, and then this is just given by all the subsets, let's say, such that the intersection epsilon different than 0. So we just check whenever the balls intersect in a non-empty manner, and from there we construct our things. So we only will have a phase whenever this thing. So to put a pair of examples to illustrate this, if we have a bunch of balls in this form, so there is this. So essentially the third complex will be something like this. Here. And we will fill that face. And if we, for example, of course from this picture one can maybe assume erroneously, okay, that if we have a bunch of points, maybe in R2, the third complex will only be two-dimensional, but one should not mislead himself or herself, because if you take, for example, 4 balls in this form, the third complex will just be, well, this is not maybe the best picture, something like this. So you will obtain essentially like the tetrahedron filled with space inside. Okay. So why is this object important? And this object is important essentially because one big theorem in algebraic topology, which is called the nerve theorem, the form that here I will essentially put is not the most general form. In general, you can prove the nerve theorem for more complicated unions of open sets and under more general conditions, but this will be enough for us. It essentially says that this guy and this guy are homotopically equivalent. So in particular, this guy and this guy have the same homology groups. The same, let's put same, whatever it means. In the sense that homology groups, homotopy groups essentially are the same for these two. So a lot of the topological invariants that we can care about this object are the same as that we care for the third complex. Here I will not enter in what it means, the homology or the shape or any of these concepts, but essentially in a way this captures the shape of, in some sense you can see this in this example and this other example that they are more or less similar. So once that we have established, okay, so we have a cloud of points, I'm able to extract topological information. Now what I want is essentially to see how I can approximate a cloud of points. So here is where it comes the second ingredient, which is the Hausdorff distance. So let's start with a motivating situation. Mind that I have here a loop. And in this loop I have this amazing cloud of points. So this loop is called S. And here we have a cloud of points that is really near a part of the cloud, really concentrated here, but that's all. In a way that we have that this distance here is small. However, no matter how you look at this, you can see in some way that this guy does not resemble. And this is used because when you look at the points of X, they are near points of S, but the points of S are not necessarily near of points of X. The way of solving this is what is essentially by defining the Hausdorff distance, which is you take two sets, A and B, and then you just consider the maximum of the supremum of A belongs to A, distance A to B, and the supremum of B belongs to B, distance of B to A. So essentially what this term is saying to you is all the points of A are near of B, And what this term is saying here is all the points of P are near of A, and this is the meaning of the Hausdorff distance. And in a way, what you will get is that the Hausdorff distance between this crowd of points and S is small, or sufficiently small. What you expect is that here you have your S, and that the points will be in a way equidistributed in some way. Maybe not equidistributed, but yet distributed enough to cover all the loop. Okay. So now it comes the more important ingredient, which is the reach. So now let's assume that S is closed inside an M. Let's not care about higher dimensional things or weirder spaces. So we have a closed subset of Rn, and what we want to do essentially is mapping each point P to P as P, where this is nearest point to P inside S. Of course, this in general is not a map. This is the main problem with PS. So the first observation is essentially PS is not well defined in general. But what one can show is that the reason that PS is not well defined, so for a particular point, this is not well defined, if and only if there is 2 points in S should start the distance of P to S, and that this is equal to the distance to the minimum point. So essentially we have S different at S tilde. So we have 2 different nearest points. Then it's not obvious which point you have to choose to project. Okay. So let's do a small example. This. Here I will introduce the definition. So the set of these points, I will call it delta S. It will be the medial set. So essentially the medial set is the set of those points that are in a way have 2 nearest points in S. Okay, so mind that we have here, if this is a loop, usually the medial set of S will be this point here. And if I have something maybe like this, probably will have some component of the medial set here, and probably will have some component of the medial set inside here. So maybe to keep it in different color. And this will be the medial set. Here this will be the medial set. So, okay, the only problem with this is if we find a point of the thing. So essentially the thing that we define in order to about this is the reach, which is essentially the distance of S to its medial set. This is called the reach of S. And the important thing of this thing is that, at least the main proposition is that for all R belonging 0 here to the reach, the map that projects from this neighborhood into S is well defined. So okay, we have this, if the reach is positive, maybe we can do something. One extra thing that here we get is that whenever this holds, we can do linear homotopy. And by doing linear homotopy, essentially we get that S and whenever R is between these two values are homotopically equivalent. So they have the same shape. And the thing that one has to ask is, okay, when this tau S is positive, and this is essentially again a proposition of Ismail and so on, is that if S is a smooth submanifold, then this guy is positive. So essentially, okay, it's an invariant that at least when it's positive, it gives me some way of approximating spaces, and it tells me like, okay, I can perturb it a little bit, it will change the shape, and thickening will not affect. I mean, this you can observe here, that if I take a little thickening, this will not affect, and it's used because I can use half a way of coming back to my original set S, because I have no point I intersect this medial set, so there is no problem in coming back to it. Okay, so once we have all the ingredients, let's go with the main theorem. This is what we see. Now we can go with the main theorem. So this was quite groundbreaking when it was done. It's essentially with this theorem. This is Niyogi-Smale-Weinberger. It says, okay, let S, let's assume close, and such that this is the important condition. If this is a cloud of points, such that the half of the distance of this cloud of points to the set S 3 times is less than 1/2 tau S. So essentially that this cloud of points is sufficiently near, and sufficiently near essentially here means the Hausdorff distance is small, and the Hausdorff distance is small in the sense that it has to be smaller than the reach. So essentially something with a bigger reach will be easier than approximate than something with a smaller reach. So then, for all epsilon belonging exactly to this interval, we will have that, okay, let's write it like S and U S epsilon are homotopically equivalent. So essentially what this theorem is saying to us, okay, you get a sufficiently good approximation, then for a sufficiently large interval, so the better your approximation is, the larger is the interval that you get, essentially you get something that has the same homotopy type as S. And this thing with the same homotopy type as S, you can compute it quite good. I think that, yeah, there is no time. So the only comment that maybe goes about the proof of this, even though, okay, we have this Hausdorff distance with reach, this thing, but when you look the proof of this theorem, at least the later versions of it, if you go to the original paper, maybe the proof is not so readable. So the main thing of this result is that in a way the only thing that you need is like a kind of elementary geometry. So you only use triangular inequality, cosine theorem, and essentially arguments of the form, yeah, if this point is near of this point, then this point has to be far, and so on. Because essentially, here the homotopy is the same one as you use here, so the only thing you have to check is that the homotopy essentially doesn't go outside our given set. But yeah, this is essentially the result I want to point out. It's not a complete result. There is a lot of sets in which this condition is not satisfied, and we would like to approximate them. But up to now, this is like the only big result that says us how much we have to approximate and how much we have to thicken the points in order to capture the homotopy type of the space.
Thank you very much. So now it's time for some questions and discussion.
Don't you mean u of x comma epsilon there? In the line, S and u of x comma epsilon are the homotopy equal to
Yeah.
So I was a little bit curious about your definition of this check complex. So just on the board in the middle. So am I correct in saying that this thing is a subset, it's a collection of subsets of X, so it's a subset of the power set. So how did you get from that definition to the two pictures just underneath it to the left? What's the relationship between this bunch of subsets? And because like the picture is sort of like intuitive.
So whenever you have this collection of subsets,
which you can always define.
This collection of subsets, the property that it has is that it's closed on inclusion. So if I have a subset and I take a subset of it, it still belongs to it. Because of course, if I intersect something smaller,
and then you draw the graph, Sorry, please continue.
Yeah, so this is what is called an abstract simplicial complex. So whenever you have a set and you have a subset of it, it belongs to the family of subsets.
Sure.
So this allows us, like we identify the points of X with the points of a simplex, and then we take the faces that are corresponding to these subsets, and this gives you a simplicial complex in the traditional sense.
Okay, so
this vectors is just a simplicial complex in the traditional sense, drawn in a different way.
Okay, so you use the check complex to get the faces.
Yeah.
Yeah, and then how did you get and I'm assuming to get the points in the line, to get the lines between the points, you just said that if two nearest neighbors in the set, like the two balls, then draw a line.
Okay, so here you have these points.
Yeah, and that's how you get the,
So first thing you do is, from the points, we choose this point. These points lie on some simplex. Assume that they lie on some simplex.
Okay.
Maybe not.
So can they just lie on the blackboard for the time being? I'm not, so I don't study geometry, so I don't really understand exactly what a simplex is. I'm just looking at the picture on the board.
Simplex means that you just take the convex sets given by the convex pool of, so from this X, you essentially pass to a set of this form. X belongs to this. So now all these are independent vectors in a way. Here you can consider what is called the simplex. This is just the convex pool of the whole set. So you consider this convex pool of points like this abstract simplex, well not abstract but actual simplex in some high dimensional space. And these simplets have some faces, and this family here just tells you which faces you have to take in order and paste together in order to get the actual simplicial complex. I mean, it takes time to see it. I mean, it's not something that is obvious, but the thing is, you just draw the vertices. Whenever two balls intersect, you get an X.
So that was the answer to the question. Sorry.
Yeah. And whenever you see that three balls intersect, it means that you actually take
and then face. And then this object is homotopy equivalent to the original collection of balls.
Yeah.
Okay, alright. Thanks.
Yeah.
So there might be other questions, but is it quick?
Question, yes, but I don't know what that.
Okay, then let me cut it now. So let's thank the speaker again.